For this video, we're going to start looking at tests that compare means. And here we're going to see a slight change in what our hypotheses look like. But other than that, the procedure we're using to conduct the hypothesis test will be the same. So let's try one together. It says the means of the number of revolutions per minute of two competing engines are to be compared. 30 engines of each type are randomly assigned to be tested. Both populations have normal distributions. The table below shows the result. Do the data indicate that engine 2 has higher RPM than engine 1? Test at the 5% significance level. So again, we're getting a nice, clear set of directions. They're telling us to perform a test, and they're giving us a level of significance. Alpha is 5% or 0.05. The other thing I'm explicitly told is I want to test the claim that engine 2 has a higher RPM than engine 1. I don't need to copy down all of my other information because they were nice in that they summarized it in a table, and this is very common. So let's start the process. Mu1 is the average RPMs for engine 1. And mu2 is the average RPMs for engine 1, or engine 2, sorry. I am going to quickly jot down, I know that my alpha is 0.05, and then I'm going to jot down my null and alternative hypotheses, and this is where it gets weird. In this case, they're asking me to compare engine 1 and engine 2, not compare engine 1 to a number. So instead of having values in my hypothesis statement, I'm looking at relationships between the mean for engine 1 and the mean for engine 2. Other than this change, the operations or relational symbols rather in between the means are the same type that we used for single tests. My null is always a statement of equality. I'm assuming the engines have the same mean RPMs. And then the claim I'm asked to test is engine 2 is higher than engine 1. So engine 2 is greater than engine 1, or engine 1 is less than engine 2. So this is a 2-sample z-test, and I know that it's a z-test because in the table I'm given population standard deviation sigma and not sample standard deviation. From here, I'm going to perform this just like I did my single tests. I'm going to draw my distribution, and then I'm going to list the calculator command and identify the values that are being used in the calculator command. So going to my calculator stat tests, the function is called a 2samp z-test. So let's take a look at what that function call asks for. Since I have stats and not a list of raw data, it's asking for the standard deviations first, sigma 1, sigma 2, and then the sample means, x bar 1, and sample size, n1, x bar 2, n2. And then it asks me for my alternative hypothesis. Mu1 is less than mu2. That's the statement I wrote for my alternative. you'll notice here, at no point do they ask me for a claimed population mean. If I scroll back up to our examples here for claims about a single mean, our t-test function and our z-test function were asking for a claimed value for the population mean. We don't see that here because we are comparing two means to each other and not one mean to a value. So let's go ahead and fill this out really quick. So engine 1 had a standard deviation of 50, engine 2 was 60. Engine 1 had a sample mean of 1500, and I was told that 30 engines of each type were randomly assessed. So for both of these ends, I know it's 30. Sample mean for engine 2 is 1600 with a sample of 30. And if I do this, it should spit out a test statistic and a p-value. And when I do this, I get a sample statistic of negative 7.01 rounded and a p-value that rounds to 0. That's telling me that I am so far out in this tail, it doesn't even fit in the picture I drew. And so the area in that tail is approximately 0. When I see that my p-value is 0, one, I know it's less than my level of significance, and I can feel very confident in rejecting my null hypothesis. So that tells me that I do have strong evidence to indicate that engine 2 has a higher RPM than engine 1. All right, let's go ahead and try another one. So this example says at age 9, the average weight 21.3 kilograms and the average height 124.5 centimeters for both boys and girls are exactly the same. A random sample of 9-year-olds yielded these results. At 0.05, do the data support the given claim that there is a difference in heights? And we can see below sample size, mean height, and population standard deviation for each of our groups. Unlike the last example, these groups aren't numbered. So I am going to call the first group in the table group 1 and the second group in the table group 2. It doesn't matter which one you call which, as long as your alternative hypothesis matches the wording in the question. As we pick through the question, I see a level of significance in that last statement. I also see, is there a difference? And I know difference means not equal to for my alternative. And if you'll hang on just a second, I'm having a brain fart here. I think that's all they gave us, so we can go ahead and jump into the solution process. So we define our variables, mean 1 and mean 2. So mean 1 is the average height for 9-year-old boys, because we define group 1 as boys. And then mean 2 is the average, I don't know why that G came out so weird, height for 9-year-old girls. I'm going to go ahead and write down my alpha since I was given that in the word problem. All of my other information in this data table here, so I don't need to copy it. I'm going to write my hypotheses. Mean 1, mean 2, mean 1, mean 2. I know my null is a statement of equality. My alternative, I am testing a claim for a difference. So not equal to. It's a claim between two means where I'm given the population standard deviation. So I want to use a two-sample z-test. So let's go ahead and draw our picture and set up our two-samp z-test. We know from the last question it's going to ask for those population standard deviations first, and then it's going to ask for sample mean and sample size for each group. And then it always, as a last step, asks about your alternative hypothesis. So we have 9.9 for group 1, 11.0 for group 2. For group 1, we have a sample mean of 123.5 and a sample size of 60. For group 2, we have a sample mean of 126.2 and a sample size of 50, and we're testing for a difference. So this is a not equal to. I got a little lazy and forgot to label those. Sorry about that. So we go to two-sample z-test on our calculator, and we enter those values. And in this case, we get a test statistic of negative 1.34 and a p-value of 0.1799, so about 1/8 or 18%. So in our graph, 1.3 something is just past one standard deviation on either side. And I can see that that represents a decent chunk of the curve, which makes sense with that larger p-value. Since our p-value is greater than our 5% level of significance, we fail to reject the null. Meaning this sample, or these samples rather, with these sample heights and these measures of spread do not provide convincing evidence that there is a difference in the heights of 9-year-old boys and 9-year-old girls on average. All right, if you have any questions about this video, feel free to send me an email or drop by office hours. Otherwise, I'll see you in our next video.